Hello everyone, welcome to this video. In this video, we are going to study about limits and derivatives, and we are going to do a lot of examples and problems regarding them. We are going to discuss it further using examples and also graphs, and I am going to discuss it from scratch, assuming that the viewer does not know much about this topic. So what is a limit? So the limit is defined in this notation, LIM, and you put a variable like x inside and give a arrow and write a real number a. So x tends to a, and this is the limit, and inside it you can write any function of the variable x. This whole statement could be read as limit x tends to a of the function f of x. Now what this means practically, let us see an example. Suppose you have the function f of x equals to x plus 1, and we want to find the limit of this function as x tends to 0. When we say tends to 0, we simply mean that limit x tends to 0 f of x would mean the limiting value of the function at point x equals to 0. Now how the limit actually works is as follows. Imagine the number line here, and let's say this is the origin. On the left hand side of the origin, you have all the negative numbers, minus 1, minus 2, minus 3. On the right hand side, you have all the positive numbers, plus 1, plus 2, plus 3, and so on. Now, we can zoom in on this part and understand what happens when limit x tends to 0 is applied. So, very close to 0, with very infinitesimal distance, we can assume there is an interval of this form. So minus 1 is further away, and plus 1 is also further away on the right. We can assume that x lies either in this point or on this point, and both of them approach towards 0. So what we are basically saying is that when a variable assumes values closer and closer to 0, the value of the function f of x changes. So we can take an example. So we can take an example here. Let us say x approaches 0 from the left. So let's say this is the point 0 and x is somewhere here. And this point P is the point where the real number minus 0.01 is there. Now what happens when x is at this point? The value of the function at the point P then should be minus 0.01 plus 1, which is nothing but 0.99. Now, if it approaches closer enough, let's say it approaches much closer, and now the new point P, which we call this one, which is much closer to 0 than it was before, is minus 0.001. Now it is much closer to 0. In this case, the required function which we are finding the limiting value of would simply be minus 0.001 plus 1. This would simply give you 0.999. And as you can understand, as the value gets smaller and smaller, this value gets larger and larger, and it approaches, as you can see, 1. Now let us try the same thing but from the right hand side. So now let's say there is this interval which we were talking about, and x is basically at this point q1, where q1 is nothing but 0.01, which is very close to 0 but not 0. In this case, the function we designed, it would be simply 0.01 plus 1, which is nothing but 1.01. Okay, this is again closer to 1, but it's not 1. Again, if we take it a little bit closer to 0, let's say at the point q2, we can say at q2 the value is 0.001, and the value of the function which we started with at this point q2 then would be 0.001 plus 1, which is 1.001. And as you can see, this also approaches 1, because as you get closer and closer to 0 from the right, the value of f decreases. With these two examples in hand, we understand that that from the right or from the left, the function actually approaches the point 1 while the point x approaches the value 0. So this allows us to conclude that limit x tends to 0 f of x, which was simply x plus 1, is equal to 1. And this is the limiting value. That is, in the case the value gets closer and closer and it keeps getting closer, if there was a case where it could get infinitely many close, it would actually reach 0. And in that hypothetical scenario, we call the limiting value has been reached, which practically it will never do. And this answer simply gives you the limiting value, which is 1, which you can also now understand that simply putting the value x equals to 0 also worked here. So the first thing in limits is a limit exists only the operation we just did here with the right hand and left hand side limit. So this is what we call an LHL, or this is what we call a left hand limit, where the value approaches from the left hand side of the required point. And this is called a right hand limit, where we approach the limit from the positive side of the number and we go towards the number and the values keep decreasing. So x tends to 0 from the positive. So this can be written as x tends to 0 minus, and this can be written as x tends to 0 plus. And this is what we have to understand. This is the LHL and RHL. And a limit exists. So we can say a limit is continuous when LHL is equal to RHL, when left hand limit is equals to right hand limit, and more formally the value at that point must also exist. So formally we can define that given a function f of x, this function is said to be continuous at x equals to a if and only if limit x tends to a minus, that is approaching the value a from the left hand side of the function f of x, is equal to limit x tends to a plus f of x equals to f of a, which is the value of the function defined at the point a. If all of these conditions are existent, we can say that f is continuous at x equals to a. We are going to use this property a lot in the problem, and in the coming parts of the section we will also explore the properties that are used with continuity and how to exploit them. Now let us talk about limits. So in general, we will assume that the limits exist, and we will say, to start off understanding the properties, that f and g are two functions such that at x equals to a, limit x tends to a f of x, and the limit x tends to a g of x exist. So we start off with this assumption that f and g are two functions such that at x equals to a, the limits x tends to a f of x and the limit of the value g of x of the function as x tends to a also exist. Now with this in hand, we can straight off the bat find out a few properties that are useful while evaluating limits. First of all, any linear combination of these two functions, that is, let's say alpha into f of x plus minus beta into g of x, should be equal to alpha into limit x tends to a f of x plus minus beta into limit x tends to a g of x. This is the first property we have, and this is the linearity property, that if fx and gx are both continuous at a, then any linear combination of them will also be continuous at a. Again, the next property we can understand like this: limit x tends to a, let's say limit x tends to a alpha into f of x is equals to alpha into limit x tends to a f of x. This is called the property where we can take out the constant that is being multiplied with the function. The constant has no role inside. So we are saying this is a constant, which means it is devoid of the function x. So alpha has nothing inside which depends on x. That is why we can take it outside and we treat it as a constant with respect to this particular limit. This is the second property which you might have already realized from the first property where we basically made this assumption of linearity. Next up, we have number 3, the product of those two functions. So limit x tends to a, f of x into gx. So the product of these two functions and the limiting value of that is simply equal to the product of the limits, which is a very cool property for us to use because we usually do not get to see this kind of properties in derivatives and integrals. Next up, we have the last property here, which is if they are divided, limit x tends to a f of x divided by limit x tends to a g of x is equal to, this is true, this exists only if obviously gx not equals to 0. So I will simply write this f of x by g of x. And this works both ways, and this works only when g of x is not equals to 0 at x equals to a. Or in other words, limit x tends to a, g of x not equals to 0. Understand that this is not what understand that this property which I just wrote, g of x not equals to 0 at x equals to a, I'm talking about the limiting value. So I should probably mention it because g of a equals to 0 really does not work out here. We just need to find out if the limit is not non-zero on the point x equals to a as x approaches a. So this is the division property. And we can move forward and do some problems on this. First, we need to understand a few important rules. So there are some standard limits that will help us in achieving this. So the first such limit, and a very popular one, is limit x tends to a, where a is an real number, and you have x to the power n minus a to the power n by x minus a. This is equal to n into a to the power n minus 1. This limit can be proved, and let us try to prove this limit. So let's write limit x tends to a, x to the power n minus a to the power n by x minus a. Now, let's call this limit ln. Now, we are first trying to understand what the simpler version would look like. So let's do this limit rather and understand how to evaluate limits at all when we cannot simply put the value. So this should be L2 should be x square minus a square by x minus a. Now, as you understand, we cannot simply put the value of xa here because if we do, we get a 0 by 0 which is undefined. But that is surely not the value. In limits, more often than not, you will always get functions inside the limits such that when you put the values inside, you simply get 0 by 0 or infinity by infinity form. In order to tackle this, we have a very simple solution. We can simply factorize the numerator into a squared minus b squared formula to get x minus a whole into x plus a divided by x minus a. If you cancel this off, you simply get limit x tends to a, x plus a, limit x tends to a, x plus a, and this value is simply equal to 2a because this is a plus a. As now you can safely put the value of limit since nothing undefined is coming, you can get 2a. So remember that you can always put the value of the limit whenever there is nothing undefined. So if the value is finite or 0, you can always put in the value and just get the answer. Okay, now let's jump on to ln. This ln can be done similarly. If you know the factorization of x to the power n minus a to the power n, this simply gives you x minus a whole into, now this whole thing can be broken down like this. So first of all, we need x to the power n minus 1, And the next term, they basically decrease like this: x to the power n minus 2 into a, and at the end you have a to the power n minus 1. This is the factorization, and this is called the factorization theorem. From this theorem, you can see that x to the power n minus a to the power n by x minus a is simply x to the power n minus 1 plus x to the power n minus 2 into a to the power 1, and all the way up to a to the power n minus 1. So there are n terms in total, and if you apply the limit over this on both sides, you can do this operation. You can apply limits on both sides. You get x to the power n minus a to the power n by x minus a equals to limit x tends to a, x to the power n minus 1 plus x to the power n minus 2 into a to the power 1, and you get up to a to the power n minus 1. As there are n terms here, and when you put the value x equals to a in each of the x's in each successive term, you simply get a bunch of a to the power n minus 1s, because you can see the powers always add up to a to the power n minus 1, even if you put a in place of x. So each of the values are basically a to the power n minus 1s, and there are n of them. And since there are n of them, we can simply write n into a to the power n minus 1. And this completes the value. This is a standard limit which we are going to use a lot. Next up, we have the standard limit number 2, limit x tends to 0 sin x upon x equals to 1. Remember this form, because while evaluating limits, we understand we need to be very careful about the format they were supposed to be originally, because limit x tends to 0 sin x upon x equals to 1. And this is valid. We will see in the coming examples that this is valid for everything where the function tends to 0, and if that function is replaced by x, we should get the same value. I'm going to quickly write down 2 or 3 more properties which are of the same type. The first one is limit x tends to 0 log of 1 plus x, where this is base e divided by x is equal to 1. And number 4, limit x tends to 0 e to the power x minus 1 by x equals to 1. So these are some properties that we are going to use while evaluating limits, and we shall do them now. Okay, let's start with some simple limits, and then we can gradually move forward. So our first example is this. Now, in order to evaluate this limit, we can use, first of all, understand that we cannot put x equals to 0 here, because that will give you a 0 by 0 format, because the numerator would simply become 0, so will be the denominator. So first of all, always try to look for the factor that makes this happen. So here root over 2 plus x minus root 2 is the factor that is making this numerator go 0. So whenever you see surds like this, always rationalize. So what we are going to do is this. We are going to rationalize this. So root over of 2 plus x minus root 2, and the conjugate would simply be like this. And you multiply the conjugate in both the numerator and the denominator, root over 2 plus x plus root 2. Once you do that, you get limit x tends to 0. And now this will come into the formula of a plus b into a minus b, which is a squared minus b squared. This would give you root over 2 plus x whole squared minus root 2 whole squared by x whole into root over of 2 plus x plus root 2. Now, simplifying this further, you will get limit x tends to 0, 2 plus x minus 2 by x whole into, now this value here, this does not contribute anything to the undefined part, so this is a perfectly finite value which is just lying inside the limit. If you find any such value which has a finite answer like 1, 2 and not 0, which is in the denominator, you can always take these expressions out. So put x equals to 0 here, and you can see that this simply becomes root 2 plus root 2. And you can see in the numerator, we have the 2's cancelled off, and the limit becomes limit x tends to 0, x by x whole into root 2 plus root 2. X will cancel off. Now X is never 0. Inside the limit, whatever the limiting value could be, inside the limit, the X's are not 0. They are simply variables and they will cut off. And what you get is this. You get the answer as limit X tends to 0, 1 by 2 root 2. And since there is no X involved, there is no limiting value required. So the limiting value is the answer itself, which is 1 by 2 root 2. And we are thus at an answer. So this answer was found out using rationalization, and there was one more way to do this. So I'm going to show you one other way to do the same kind of problem using the property we just learned. So write limit x tends to 0 root over of 2 plus x minus root 2 by x, and now substitute y equals to 2 plus x. I'm showing this to make you understand that we can substitute in different variables and change the limit accordingly to our own needs. When x was tending to 0, thus y will tend to 2. To find out what the new variable tends to, just put in the value of x, previous variable, and you should get the answer. So this limit now turns into limit y tends to 2, and now root over 2 plus x simply becomes root y. This becomes root 2, and x from this equation would become y minus 2. So this is y minus 2. Now if you write this again like this, limit y tends to 2, and you write it like y to the power half minus 2 to the power half divided by y minus 2. Now this is reminiscent of the formula we just used, where we had limit x tends to a, x to the power n minus a to the power n whole divided by x minus a. So we just simply have the limit here in terms of y, which is the same thing. The answer of this was a into n to the power a minus 1, right? So this would be half into 2 to the power half minus 1 directly from the formula. And this would give you half into 2 to the power minus half, which is nothing but 1 by 2 root 2. And thus we are completed with the answer. Let us evaluate another limit of the same kind. Limit x tends to 0, and now we rather have sine of 2 plus x minus sine of 2 minus x by x. Again, if you notice, if you put in the value of x equals to 0, it will give you a 0 by 0 form. So again, we need to do some adjustments in order to find this value. So what we can do is this. We can try and utilize our formulas, and then we can understand what to do with this. First of all, sine A minus sine B can be found out using the rule of product to sum to product, right? So remember the formula, sine A minus sine B can be written as 2 cos of A plus B by 2 into sine of A minus B by 2. Using this formula, we can write 2 cos of 2 plus x plus 2 minus x, which is basically 4 by 2 into sine of 2 plus x minus of 2 minus x, which is 2x by 2 whole divided by x. This gives us limit x tends to 0, 2 into cos 2, and we have inside sine of x by x. Since this is a constant and we learned in the properties, the constant simply comes out as a multiplied version. We simply have the answer 2 cos 2 into limit x tends to 0 sine x upon x. And this is our required answer. Okay, so this would give you 2 cos 2 into 1, because this is the standard limit, and the answer should be simply 2 cos 2. Now let's do another example. The actual formula that we learned was this: limit x tends to 0 e to the power x minus 1 by x equals to 1. Now we are going to try and apply this formula, but we have to adjust for the terms. What I mean by that is this: we can first of all take out the 1 by 3 that is lying inside the denominator, since it's a constant and it is basically multiplied with the whole limit. Our limit becomes e to the power 2x minus 1 by x. Next, you have to notice that whatever the power was e had the power x, and that is why in the denominator there was x, and here it was x tends to 0. You have to adjust for the same thing so as to get the same format, otherwise the value would not equal 1. So what we can do is we can bring an extra 2 in the numerator, and we can adjust for that in the denominator like this: e to the power 2x minus 1 by 2x. And since x tends to 0, 2x must also tend to 0. So this limit can simply be written as limit of 2x tends to 0, where we have e to the power 2x minus 1 by 2x, and now it exactly matches the form. You can also substitute for y equals to 2x to get this format. Once you get that, you simply have the answer 2 by 3 into 1, which simply gives you the answer 2 by 3. So this is called adjustment. Let us see another problem with this. Again, to evaluate this kind of limit, we are going to use the standard formula of limit x tends to 0 sin x by x, and this would give you limit x tends to 0 sine of 5x by x, first of all, because we are trying to get the same formula, and then again we have sine of 3x by x. Now, we understand that these two limits in the numerator and the denominator, even if evaluated separately, the denominator is not 0 when found in the limit, because it would be something, because we know sin x by x is 1 in the limiting value as x tends to 0. So sin 3x by x is not going to be 0 at least when x is tending to 0. So according to the division rule, we can separate them and write them as separate limits like this: sine of 5x by x whole divided by limit x tends to 0 sine of 3x by x. Now, what we can do here is this: we have to again adjust for the 5 and the 3 so as to get the perfect form for sin x by x. So we can multiply a 5 outside, and we can write sine of 5x by 5x divided by 3 into limit x tends to 0 sine of 3x by 3x. And now this limits equal 1 because they are in the standard form as they should be. So the answer basically is 5 into 1 by 3 into 1, which is 5 by 3. In the next part of this series, we are going to discuss limits where series and also derivatives will be involved, and we will also learn derivatives from scratch. Once we are done with derivatives, we can apply L'Hopital's rule to evaluate limits and also Taylor series expansions and do a lot of problems which have difficulty ranging from easy to difficult, at least 5 problems per topic, and ultimately we can move on to integration. So let me know in the comment section if you like this idea of the series and you want me to continue this. So I will try and bring these detailed videos every time now. Thank you again. If you're new to the channel, please do subscribe.